Now we have Shawn Tabrizi, who will be giving a presentation on getting started with XCM, your first cross-chain messages. Shawn?
Hey there, Bill. Thank you so much for having me. So yeah, today I'll be presenting a workshop on XCM, and definitely this will be a very interactive, very communicative workshop. So I have the chat actually open here with me. So definitely, if you ask any questions, you can see it there. I also have Bill, who's said he would be happy to jump in and ask any questions when there are some. As an overall kind of goal of this workshop, my goal is kind of to walk you through XCM. So XCM is I would say like a very dense onion, right? You have to peel back a lot of layers to understand kind of how it works and how it all goes between different chains. And so what I was looking to do through this is kind of walk through all of the primitives of XCM. And then I was looking to maybe even run through the code and continue to peel back the onion deeper and deeper so people can kind of navigate and walk through it. And I think at some point, what I would like to do is I would actually like to go, after we've gone through some of the material here, I'd actually like to go through the repository and be able to look at, what are the different things and structures inside of there. How can you, as a person who's developing on XCM, understand how you can navigate the code base, understand the terminology, all that kind of stuff, in order to build your own parachains, do your own messages across different chains. So yeah, that's kind of the main thing. So let me pull up my screen here. Okay. And so again, I have a little bit of material I want to work on. I'll be again starting with all the XCM primitives, and I'll be touching all the main types of. I think that's the most kind of common scenario for XCM. So we have basically a simple transfer on a single chain. We have a reserve-based transfer and a teleport transfer, right? And so I'll be walking through all of those things. Again, feel free to ask any questions. Bill, also feel free to jump in if there are any main questions coming up. And then again, at the very end, I'll be looking to potentially walk through some of the code base, unpack more and more of that stuff. To note, there's a lot of great resources in addition to what I'm working on here. So you can, of course, Gav wrote, kind of a 3-part series on XCM, which is a really great introduction, kind of the thinking model about how we designed it and kind of what we built. There's, of course, this repository, Parity XCM-format, which is the formal specification for XCM, which was just recently updated for version 2. And then, of course, we have the code itself, and the code has a lot of comments and notes inside of there. So really, we encourage you to jump in there. And so one more thing to note, coming from this, is that this workshop is definitely oriented towards kind of like more hardcore developers. Again, I think that the more closer to advanced of the intermediate level. So really, what we encourage is to become familiar with the source code, such that you can make all the decisions you want to make about configuring your XCM platform correctly and accurately. It is easy to kind of copy and paste some of this stuff, but really the more of an understanding you have of XCM and configuring it, the more powerful you'll be able to do different kinds of messages and have different kinds of workflows and handle different kinds of feeds and all that kind of stuff. So anyway, let's jump in. Is there a link to my current page? Yes. Let me see. If you actually go to, it should be shawntabrizi.com/XCM workshop. It should be up to date. I will say that I didn't proof this super heavy. Yeah, I think in the chat. So definitely probably lots of typos, probably some little bit of errors, but it should be no problem for doing our live workshop right now. Okay. But feel free to go take a look at that and follow along if you want. Okay, so first, very meta. What is even an XCM? Well, an XCM is a message. Oh, actually, this would be a great place to start. Let's start the glossary. So XCMs are messages. So it's an acronym for a cross-consensus message, and the use of consensus here is really trying to define the fact that these messages can go not only across chains, so it's not just cross-chain messages, but can even go across different consensus machines. So you have bridges, smart contracts, all these other kinds of platforms. And so XCM is meant to be kind of a high-level language for these different consensus machines to communicate with each other. Now, you can imagine that, again, XCM itself has built a lot of abstractions within it, to be able to support kind of any level of messaging you want across these different consensus machines. Like, 2 different contracts may have very specific kinds of messages they want to send to each other. But the idea about XCM is basically to capture all of the most common scenarios of XCM and define them well. So, in this world of blockchains and consensus machines, doing things like balance transfers is very common. Withdrawing and depositing assets is very common. So XCM has defined a standard format for those kinds of messages. So you can imagine we have a list of all the most common kinds of things you might want to do, and we've defined that in this format called XCM. And then on top of that, you can, of course, add the flexibility and customizability of things like, generics and Rust and all this kind of thing that we provide to be able to allow you to do more generic messages. Now, how do you actually go and send XCM messages? Well, this is using something called XCMP, which is the cross-chain message passing. And this is a Polkadot specific protocol. So whereas XCM isn't really specific to any kind of platform, XCMP is a Polkadot specific kind of mechanism for transferring messages. And XCMP is broken up into kind of two pieces. One is this, the cross-chain message passing, which allows, two different parachains to talk to each other. And then the other is the vertical message passing, which is basically messages between the relay chain and parachains. So we have these things called downward messages, so DMP. And these downward messages basically allow you to go from the relay chain to a parachain, hence the message is going down. And then we also have UMP. UMP is upward message passing, which is how you can get a message from a parachain up to a relay chain. So these are all the kinds of different the directions of a message can go. So you have an XCM message, it can go from a parachain to a relay chain, from a relay chain down to a parachain, or from a parachain to another parachain. And then you can imagine that you can even have like chaining effects, right? So let's say, for example, you want to imagine in the future of Polkadot, we're going to have multiple different parachains. You're going to be able to have one relay chain or one parachain send a message to the relay chain. The relay chain sends a message to another relay chain. Then the relay chain sends a message down to that parachain. So you're going to use a combination of these different XCM, XCMP, DMP, UMP, all that kind of stuff to be able to transfer everything around. Okay, so that's just a little bit of the terminology here. Let's go back to the instructions. So what is an XCM then? So an XCM, again, is that message. And in terms of definition, oh yeah, if it's too small, I can also increase this the size a little bit. Thanks, Dan, for calling that out. But XCM really, at a certain level, is just a vector of instructions. So these instructions are these individual kinds of messages or instructions that you can basically have different people execute. And so when we send an XCM message, you can think of it as like basically a set of steps. Like, please follow these steps as much as possible. If there's any errors, stop the message and return an error. Otherwise, complete all the steps in order. And instruction of this message allows you to do lots and lots of things. So you're allowed to do certain instructions that can help set you up for future instructions that are going to happen. One thing that's important is that in terms of like the Rust side, these instructions are actually generic over call. And call here is actually referring to the call enum that is for the receiving chain. So you can imagine if you want to do very abstract kind of instructions, like this is the most abstract one, it's called a transact. A transact here allows you to be able to basically execute any arbitrary message that the receiving chain is able to support. So just like right now, you can go to Polkadot and you can, as an individual user, submit a transfer call, do a democracy proposal, do a staking option. All of those, and of course, as we add new palettes to Polkadot, you're going to be able to add more and more calls. We can't just continually expand XCM to have more and more things. So what we do instead is expose this transaction, which is generic enum, which means that whatever calls are supported on your chain, you're able to send a transact XCM to be able to target those messages. So again, the idea here is that on top of all of the most basic commands that we understand, you also support this generic transact. Now, the good thing about having these generic commands is you can imagine over time, you might have upgrades to palettes, upgrades to syntax, upgrades to formatting that's specific to your chain. But what's nice is XCM acts as, again, a layer before you actually touch the runtime or touch the downstream code. So if you have an instruction like withdraw an asset or transfer an asset, right? We can actually allow XCM and have you as a programmer programming XCM on your chain build the abstraction such that this XCM message stays consistent, but behind the scenes, palettes can change, formats can change, all these things can change. So you can still have a consistent interaction with other parachain levels, but not have to worry about breaking changes at the XCM level. And this is, again, the benefit of having a well-defined format of XCM. Now, of course, if you were using transact, what you would be worried about is that if you're interacting directly with another chain and that chain does a runtime upgrade, and for whatever reason that runtime upgrade breaks the transaction format, you'll have to make sure that your transact calls don't break in the meantime. Like, this is where there is an opportunity for these transact calls to break. But again, we suspect that these kinds of transact calls will only be used in kind of very specific, tightly coupled, parachain communications. And again, the majority of the communication you're going to have between different parachains and relay chains and all kind of stuff is all going to be through these more generic XCM instructions. And so here's at the bottom is a quick example of what an XCM message might look like. So you have, a vector of instructions. Those instructions have some inputs into them, and even you can have nested inside of an instruction more XCM messages, which can be used as part of the execution. So we're going to talk about that next in the XCM Executor. Okay, so now we have the message. Now the message itself doesn't do anything. It's just a message. It's just, when you actually go ahead and serialize it, it's just some bytes. In order for us to actually execute the message, we have this kind of, virtual machine, I would say, called the XCM Executor, which is inside of, Polkadot, inside of your chain, all that kind of stuff. It can actually go ahead and process these messages. Now, I guess one thing to note is that, if you wanted, of course, write your own XCM executor, that's not really a great idea because your XCM executor should probably follow the specification of ours, and there's a lot of niche details. But we provide for you within Polkadot a kind of template XCM executor, which can be configured and has all these different states in it, which basically allows you to really easily add this XCM virtual machine into your runtime in an easy way, and again, a very configurable way. One of the things that's important to know about the XCM executor, again, is there's a lot of internal state. So you can see here within the XCM executor, we always keep track of this thing called the holding register. And the holding register is like a virtualization of assets, which the XCM can actually use. So you can imagine that you as a user, you have an account on the chain with some balance inside of it, right? And what we're actually going to do is we're going to actually, when you actually start doing XCM messages, some of the first instructions that you're going to actually operate on are probably some things like withdraw asset. And so this withdraw asset, what it will do is actually take an asset, pull it out of your account, just like, you would be transferring it to another user, but instead you're kind of transferring it to a virtual holding register. And the holding register processes those assets, keeps it in memory, and then allows you to do lots of operations on those assets. So a lot of the instructions within XCM don't act on your account and your balance directly, but act on this holding account. And there's only a very few set of messages which actually allow you to pass the assets from your kind of real account to this holding account. But on top of that, there's a bunch of other state items inside of the XCM executor, which you can see here, like, the origin, like what is the current context of the origin that I should be processing a message with? What was the original origin? Where did this message come from to begin with? We have some configuration things. If there's an error, we can keep track of those errors within the state. Any kinds of weight that we have used, or any weight credits that we have. And of course, any other kinds of things, within the XCM state. And so one of the things we'll be doing is we're actually going to be running and executing some code to see how the XCM executor actually executes. And to do that, what we'll be doing is actually adding some logging. So I'm going to go, whereas the XCM executor right now doesn't have any logs, and I'll show this live too. But I'll be going ahead and adding some print line statements so we can actually see the XCM executor execute a message and actually go through the stuff. And you can see at a high level, the input into the XCM executor is this function called execute. And it executes very simple. It actually just goes through the XCM message, iterates over all the instructions. Remember, the instructions are just a vector, although the XCM message is just a vector of instructions. And then we try to process each instruction one by one. So really, when I'm looking to add this logging, I'm actually adding it to a process instruction, which is actually going to actually execute the individual thing. One more thing before we actually get into writing some code, I want to talk about the XCM configuration. So the XCM Executor obviously is a virtual machine which can execute all this stuff. But the XCM that you might want to process for your chain may be different than the XCMs that another chain might want to process. Or the behavior you want to have of XCM may actually be different between two different chains. So the way that you can actually get the XCM VM, the executor, to actually behave in the way that you want it to behave is to use this XCM config. And actually, if we take one step back real quick on the XCM executor, you can see the XCM executor is generic over this config, right? So this config basically has a bunch of different little, tinker and knobs that you can go ahead and use to adjust the XCM executor's behavior. So let's actually, I have here a list of all the different configurations. We can actually just talk about a few of them. So here we have the XCM sender. So the XCM executor itself doesn't actually send messages between parachains. Remember that the XCM protocol itself is actually the XCMP protocol is specific to Polkadot. But I guess at this level, XCM really isn't specific to any chain or protocol. You can use it for anything. So you can imagine having an XCM sender in Polkadot configured to use the Polkadot protocol. But you can imagine that, configure it for a different chain or a different setup. You can actually adjust the XCM sender. We provide some UMP and DMP and XCMP palettes that people can use out of the box. But even if you wanted to have your own custom palette which handled sending XCM messages, or to create your own meta protocol, for example, if you wanted to have your own meta message transfer system between your multiple parachains, you could go ahead and define that too and still use XCM as the platform for those messages. So it's really some really powerful stuff. It'll be actually interesting to see, in 2 or 3 years, how deep people actually go into actually customizing and doing their own custom stuff. So that is nice to know. Then we have things like, okay, let's look here. Is teleporter or is reserve. Here, these are ways for users to configure different locations or different basically message locations as being acceptable for handling reserve transfer, teleport transfers, etc. So here I can say I will accept a teleport transfer, and we'll talk about teleport and reserve transfers more in the future. But I'll accept this kind of transfer from parachain 200 and 300. But I won't accept it from parachain 400. For parachain 400, I'll accept these kinds of messages. These kinds of filters you can add to your chain to support different kinds of message passing. You can even have one that says I accept all messages from anyone, or I accept no messages. These filters basically allow or gate access to different kinds of XCM messages and instructions within your XCM. Let's do more. We have barriers. These are like a set of filters. When you get an XCM message, you might want to filter out certain kinds of messages which you don't want to support. Or let's say that you're doing a runtime upgrade and you want to make sure for a short period of time while you're upgrading, users don't send you the wrong kind of message. This barrier can allow you to basically filter out any kinds of incoming messages and verify should this even execute internally, right? We have weighers. Of course, weights are always a thing in any types of, blockchain system. If we're going to be doing work on your chain, you better, one, know how much work you're going to be doing, and two, pay us for that work. So things like weights are going to be able to handle that. We have subscription services. So, we have this way for you to subscribe to other parachains and other XCM systems. So if they upgrade their chain, you can actually be notified of those upgrades. And again, configure all that. So you can see here, there is so much to talk about here. And I think at the end of this talk, with our extra time, I'll be going through and actually diving deeper into each of these different configurations. I did want to quickly show you what a configuration might look like for Kusama. So here's the configuration for the Kusama runtime. So you can see, for example, here, we don't support any reserve assets coming from other places on Kusama. But maybe if we supported a bridge between Polkadot and Kusama, you might see that change. You might actually see us accept reserve assets from Polkadot, right? You can imagine the Kusama treasury would accept the DOT token into its holdings. That's very exciting. We do have some trusted teleports, and that's configured down below here. So, obviously a lot of these are just variables, which are expanded more down here. But you can see things here like trusted teleports. So here we handle the teleport for Kusama for statement. So we support teleporting assets from Kusama to statement and backwards. And so this kind of behavior, again, what we should know about statement is basically an extension of Kusama. That these aren't separate parachains like, for example, Kusama and Akala or Kusama and Moonbeam. Statement is actually just an extension of Kusama, which lives on a parachain. And so in that case, these two are trusted together, and we're able to have a teleport between the two of them. Let's look at this. So look at the barrier. So we have things here like, we allow an unpaid execution from child system parachains. So as I mentioned, statement is one of those system parachains. So between Kusama and statement, they don't actually need to pay for those interactions with each other. That any of those messages are trusted. And so any of the fees or any type of payment mechanism, it could be handled before the XCM message is actually processed. And we allow within the barrier saying, hey, we allowed that a message from something like statement doesn't need to be paid for. And so I don't want to dive too deep into this. I mean, you can, it's a big onion here. We're peeling back the first layers here, but you can see there's so much configuration you can have here, which allows all of this to be processed correctly. Yes, statement is a system level parachain. And I guess, I can talk a little bit more about system level parachain. So kind of the high level idea here is you can see that Polkadot and Kusama both have a lot of different, statement and state mine, sorry. But Polkadot has a lot of different functionalities on it, right? So if you use Polkadot right now, its core functionality should be supporting parachains, supporting the connection and interaction of parachains. But on it right now has staking, has democracy, has balances, has a million different functionalities in there. And in order to optimize Polkadot to make sure that all of its resources is doing its primary purpose, in the long term, what we're going to do actually is going to take all of these different functionalities and move them into system parachains. So you can imagine that having staking on its own system parachain, democracy on its own system parachain, etc. And all of these system parachains, again, are going to have a different kind of relationship to Polkadot than the average parachain. As we know, onboarding new parachains is a completely permissionless process. Any team can go prove their worth to the whole community, go through a parachain auction, the crowd node system, and onboard. But we don't actually, Polkadot shouldn't trust any of these parachains, right? All these parachains, we like you, but we don't love you yet. You're not really, family, so to speak, right? But these system parachains are written by the same developers and the same maintainers of the core Polkadot runtime. So we can have a different relationship with these parachains. We can have things, for example, this is crazy if you think about it. We can have a governance parachain, which it decides the upgrades of the relay chain. Think about that. Think about a parachain of Polkadot, which controls its governance, which controls its upgrades, which controls its logic. That's kind of like a next level meta thing, right? But this is actually the kinds of things we'd be looking to do. And so when we look to scale Polkadot further and further, we want to eke out every single possible transaction per second or every single possible parachain we can support. Doing things like transferring these different system functionalities into system parachains is how we're going to be able to do that. And again, it's important that within XCM and the configuration that you're able to identify, these not so safe parachains with these safe parachains and be able to have different kinds of behaviors. Hey, I don't need to pay fees or pay any execution costs for a system parachain. Yeah, hopefully there's some mind blown there kind of stuff. Okay, so let's actually now, we talked about things at a little high level. Let's actually go and try to execute some stuff. So what's been really nice, and this was actually a community contribution from the Akala team, they introduced XCM Simulator, and this makes it really easy on a single computer, on a single chain, even within a test environment to be able to actually simulate XCM messages. And so what I'm going to do is I'm going to be using this XCM Simulator, be doing some logging within the XCM Executor to kind of get a feeling of what's going on inside, right? So do me a quick, I'm going to go back real quick. We're adding log section on the XCM Executor. And I'm going to go ahead and copy this, just a little bit of copy. And then I'm going to be going into the Polkadot repo. So again, if you want to do this too at another time, you can, of course, just clone Polkadot repo. I'm on master right now. And basically, I'm going to go into, let me go in here. Let me also make things bigger. It's a little bit hard to work with things so big, but I mean, hopefully this is a good compromise between size and my sanity. If you go within the Polkadot repo, all of the coolest stuff we're going to be talking about today is inside XCM. What I'll be looking to do is actually go inside of the XCM Executor, go into the source, go into the lib.rs, and here's where we define the XCM Executor. So as I mentioned before, there's this execute function, which its purpose is basically to iterate on instructions and process them. And so the actual cool logic we're interested in is in this function process instruction. And if we take a quick look at this process instruction function, you can see here there's basically a giant match statement. It matches which kind of instruction we want, and each instruction has its own logic built into it on what we want to do to execute, right? So if we do a transfer reserve asset, we match into here, we have the inputs, and then bam, we're going to do a bunch of logic specific to this instruction. So this is like a very simple state machine kind of thing. What you can also see really quickly into here is the use of the config again, right? So things like all this XCM configuration, the way we're able to allow you to manipulate the XCM executor through these configurations is by using these generic parameters, these configurable parts into the actual executor instruction processing itself. So when I do things like, let's find a good example here. When I have an instruction teleport asset, I'm going to have here a check ensure that the configured is teleporter matches the origin and the asset that I'm processing. So you in the outside, where you actually set up your XCM executor, configure, here are the assets I support and here are the origins I support them from. And here we will actually do the check for you. Is the thing you configured set up correctly? Like, does it match like what we accept? If it does, we will actually go ahead and actually process those extra messages. If not, we'll say it's an untrusted teleport location. So at that level, you can actually really, if you really want to understand how all these configurations work, you can jump into this code and actually follow and see, okay, well, I configured this thing here. Okay, it's being used here. That's processing this. I might get this kind of error message, etc. Right? So our first kind of dive into this XCM process instruction is actually going to be by adding some logs here. So what I'm going to be doing is right now, this returns a result, and that comes directly from this message. So I'm going to capture that result so I can actually do things before it returns. So let result equal here. I'm going to write some simple logs. So these are just print line instructions. Of course, I can do print line. Like obviously, everything inside of XCM also is no STD. In general, you can't do print line, but I'm going to be running tests, and that all is within the XCM environment, right? Or within the STD environment. And then at the very end, I'm going to do a holding. So this is the end of that processing. Oh my God, there's so many messages. Here's the end of that processing. I'm going to look at the holding after, right? And then I'm going to return the result. Okay, and then I guess just to remind users here, what I'm doing here in terms of logging is I'm actually taking a look into the self. So when I process an instruction, all of this is on this XCM executor state. So remember I mentioned already that XCM executor has all of this state inside of it, right? So as we're processing a message, it's keeping track of what's the current error, what's the current origin, what's the current holding, all that kind of stuff, right? And so I'm actually able to peek by doing things like here, like, look at the origin. I just call self origin, look into the XCM executor state to see what the current origin is. Same thing with the holdings. The holding is the kind of the most interesting part of this kind of stuff. Okay, so now I've added these log messages. Now I'm going to go ahead and execute the thing that I want to execute. Let's move some windows over. So the first test is a simple transfer. So this simple transfer is quite simple. Of course, it's simple. Basically, what we're going to be doing is we're going to have a parachain send a message to the relay chain saying, hey, move some assets from my sovereign account into the sovereign account of a different parachain. Let's quickly talk about what a sovereign account is. So a sovereign account is basically an account which lives within the consensus system that we're dealing with. So if let's for more specific terms, let's talk about like Polkadot and let's talk about statement, right? So on Polkadot, you all have accounts, but statement also has a specific account with a specific prefix. It's like parachain ID, whatever it is, and you turn that into an address, and that's the address for statement. That means that statement itself can actually hold assets and manipulate assets on Polkadot via XCM. So what we'll have to do is like say, okay, well, statement has some tokens on XCM on Polkadot, and we're going to go ahead and try to transfer to another parachain. Let's say parachain 200 or some other parachain. And basically, the message will come from the statement parachain. The relay chain will be able to say, oh, this message is coming from the statement parachain. This means we can allow it access to that account, and we can actually execute the transfer via XCM. And so let's take a quick look at what that looks like. And while we're doing that, we're going to take a quick look into the XCM simulator as well. Actually, I'm just going to run the test first. We can actually dive into it. I think it's better to see the results first. So let's run this test. A little bit of compilation. No big deal here. By the way, I'm right now running everything on a MacBook Air, actually, using the M1 chip. And oh my God, I had the choice between using my really, top of the line MacBook Pro or using a MacBook Air. And the MacBook Air is actually faster for some of these things, man. So I can't wait for the next M1 chip to come out. Okay, but here we are actually executing this test, and the test, of course, is the transfer, and we can actually walk through it. We can see that these log messages show up, right? So the first instruction is withdraw asset. We can see the origin where it came from, so it's coming from parachain 1. We can see the holding before. There's no assets in the holding. The holding after, here we're withdrawing an asset. You can see that now we have some assets inside of the holding. And then we execute the next instruction, which is buy execution, so pay for some wait stuff. Again, we manipulate the holding. And finally, the last instruction is deposit asset. So we're depositing the asset into a new place, into parachain 2. You can see here. You can see the origin, again, is from parachain 1. The holding before has some asset, and the holding after, nothing is there. So you can imagine to do a transfer, a simple transfer between parachain 1 and parachain 2, we took some asset, put it into holding, and then put it into the other parachain. So we basically did a withdraw deposit. Very simple. Now let's actually go take a look at this test and kind of see what we actually did in the background. So I will search for withdraw and deposit into the code base. Cool. Yes. And so you can see here, this is within the XCM Simulator example. So let's look at that. We can see here, within XCM Simulator example, there's this librs, and we have this test, which actually goes ahead and executes this message. So I'll show you this first, and then we'll actually go into the XCM Simulator just a little bit more so you can understand how everything's going. Am I talking too fast, Dan? Let me know. I'll try to slow down. You just tell me, Dan, if I'm talking too fast. Yeah. So okay. So withdraw and deposit. So here you see that we initiate the message starting on parachain A. So this is like parachain 1, right? And here we are going to be forming a message. And of course, it's very simple to do a transfer: withdraw, buy execution, deposit. And then we're going to send the XCM message to the parent. This is the relay chain. Oh, good. You're talking about the M1 about me fast. Okay. As long as I'm not talking too fast. But still, at some point, we all know what's going to happen. I'm just going to, start rapping. So definitely hold me down. Okay. So we're going to be sending it to the relay chain. And then within the test, we're able to actually verify the state of the relay chain. So what's the beauty of this XCM simulator is what it does is it actually allows you to execute functions within the context of parachains and relay chains. You can actually produce multiple of them. And then just have that all execute. So this was, again, a really great contribution from the Akala team, specifically another Shawn out on the Akala team. And so we actually dive just a little bit deeper into this. We can actually see above, there's some very beautiful macros which define the different parachains. So here we have parachain A, which has parachain ID 1 and has all of these configurations here. Parachain B, some more configurations, the relay chain. and we can define a network, right? The network has a relay chain here and a vector of parachains. So this macro does all of the magic for you for setting up like a simulated XCM environment. And then within the actual code of the XCM simulator, you can see that these macros expand to do a bunch of things, which handle like DMP messages, handle XCMP messages, handle all the different kinds of messages, like UMP messages here, and simulates in the background exactly what it would happen if you were actually doing XCM messages across a real network. So this is, again, a really powerful tool that you can even inspect all the state of all the different parachains and stuff like that, all happening in one spot. So again, a very powerful tool to use. You don't need to dive too deep into this half of it. Just know that, again, it's very easy to mock up a network environment and to write tests which do all this stuff. And so when we go and actually execute that withdraw deposit test, we are just executing this message, and we're able to see all the different behaviors of processing those instructions, right? Yeah. And so then we see the output. And again, I think I'll see that we're populating this holding. So now let's talk more about kind of the layers of the XCM executor, right? So before we would even execute any message, we have this barrier. I think I talked about this a little bit before. And this barrier is one of the configurations within the XCM executor, which determines whether or not you should even execute a message. Now, again, the important part of kind of the wait and execution strategy of Polkadot is that, how do I say this? Unlike smart contracts, again, where we would actually take a transaction from a user, and we would start processing the message immediately, and we would just keep going until we ran out of gas, right? And if we run out of gas, we return an error, and then the message is all unwinded, right? A few things that metering the gas such that every instruction, we say like, okay, you did a plus sign, add 1 to the meter. You did a minus sign, add 2 to the meter. You did a multiplication. You like every single instruction within the smart contract environment that's metered that way has to be, adjust the metering of how much weight you've used. And this is very expensive. You can imagine literally every single addition operation is multiplied by 2, right? You have to do 2 additions for every single, modification. And so this over larger and larger messages becomes very heavy to the system and very inefficient. Furthermore, there's also a lot of implications in terms of efficiency that we're able to have when we know that we can actually execute a message completely and have it, just execute completely and correctly. And of course, we can also optimize things for like fees or, have certain handling and management for different kinds of users all in this kind of way. So the same thing with XCM messages. We want to, before we actually start processing the message and actually start doing work, we want to actually just take a quick look at the message from a high level and say, does this message even make sense to execute? For example, we could have a barrier which says, we don't accept XCM messages. Like, yo, don't talk to me. Like, this could be a brand new parachain, is still onboarding, still hasn't had the latest upgrades. We can make sure it says like, hey, don't send me messages. Like, I won't accept any messages. Or you could have a barrier which says, I only accept messages from my like 2 favorite parachain teams. I won't accept messages from anyone else, just my 2 favorite ones. So without having to do any heavy computation, we can just quickly, accept or deny different barriers. But even more than that, we can use barriers to actually investigate whether a message will attempt to pay for fees. So one of the hard parts about these cross-chain messages is that I'm sending a message to you, I'm asking you to do some processing on your side, and you are the one who who has to do the work. So somehow I should be paying you for your time. But how do I pay you if I don't, if you don't start processing the message? Like a chicken and egg scenario here between processing the message, which is going to have the the payment for you, and knowing that I'll pay you at all, right? So what we can actually do with these kinds of barriers too is actually go and look at the message and say, hey, is there anywhere in this message some expectation that I will get paid, right? And if there isn't, I'm not going to accept this message. So let's take a quick look at some of these different barrier options. So again, this one is the feeless XCM barrier. So this barrier says allow unpaid execution from. So we already talked about this with between Kusama and StateMine, or Polkadot and StateMint, that between system level chains, it's okay to say that we don't allow any unpaid execution, because we can assume that that chain takes the fees on that side. And again, these system level chains are just an extension of the relay chain. So here, basically, I say, does this origin match what I expect in this generic parameter? If so, then accept the message. We don't care anything else other than the fact that this message is coming from them. And that's basically, and you can support basically feeless messages, because you can have XCM messages which have no message inside of it that actually takes a fee. You can still accept the message. But a more common message, or a more common filter that you would apply to most of the other parachain teams, ones you don't trust necessarily, is allow top level paid execution from, right? And here you have is again the should execute, which is the barriers trait, and we can go through it and we can say, well, I will look at the message without actually executing the message. I will make sure that in a sane way that there is some by execution somewhere inside of it. So basically what I'll do is I'll look at the message, I'll iterate over it, and I'll make sure there's at least there's one of receive teleport asset, withdraw asset, reserve asset deposited, or claim asset. These are the kinds of instructions that are right now in the XCM Executor that can populate the holding register. So as we kind of saw already, when you do withdraw asset, we move asset out of a user's account into the holding register. In the holding register, now it can be used for fees. Same with receive teleported assets. If we want to teleport assets over there, we of course verify that the asset can be teleported. If it can be holding register, and now again it can be used for fees. These are the kinds of things that these messages support moving things into the register. So first we check, okay, is there one of these kinds of messages? Then we skip any clear origin. So that's a message that doesn't really, it's like basically no work, and we basically, it's not something that's super important. But then we say the first message after these messages, or the first instruction after these instructions, should be by execution. If you're asking me to do anything else before you pay me my good fee, sir, I'm going to throw away your message. So this is, if we go back to actually our first example here, the instruction here is withdraw asset, buy execution, deposit asset. If I tried to do withdraw asset, deposit asset, and then buy execution, we would say, no, sir, I will not deposit an asset until you've paid me my fee, right? I will not do that. And so this is the same kind of logic that you can imagine with any kind of execution here, that sure, I will do a little bit of work to make sure that I get some fees into the holding register. This is kind of unavoidable, but I will not do any more work until I see a buy execution here. And I see a buy execution for a certain amount of weight that you expect the rest of the message to take, right? So I will give you credit for this much weight that you want to buy execution for. I will make sure I can take that out of the holding register, and then I will actually go ahead and process your messages, right? And so this is a really key part of, the barrier acts as a sanity check for this kinds of processing before it actually has to do any heavy work. But yeah, and again, if you actually imagine this a little bit further, this is super powerful, that within the XCM protocol itself and within XCMP, we don't actually put hard limits on how you want to take fees. You can imagine that by execution here, of course, can be .token. .token has a certain, price, or has a certain, corresponding value compared to other tokens, and we can pay for weight in that way. You can imagine paying for XCM messages using a bunch of different assets. Imagine a DEX, right? A DEX could have a relationship between all these different assets. So you can actually look up what is the relative value of an asset and go ahead and pay using a different asset. Or you can imagine having some kind of like token system or credit system. Like I allow this parachain to send me one message every, every month or every week or whatever, right? And I will support, a free message once a week. And I can program all of this logic within the XCM Executor and within the XCMP system to be able to support all of these different behaviors. And so really, from taking a free before we do anything to taking no fee at all or anywhere in between, we support these kinds of things. So really, I imagine that, XCM and XCMP is going to, really have an exploration phase over the next 2-3 years. Okay. So we talked about by execution. What does that look like, right? So by execution, within it uses one of the configuration traits of the XCM executor called the trader. And the trader will basically, the buy execution has basically two things. Like here is the asset which I allow to use for fees, and here's the amount of weight I want to pay for. Tell me if I can pay for it. And so the trader is really the one which will go ahead and do and purchase and try to make that weight purchase. And if the trader is successful, what it will actually do is populate the XCM configuration, the XCM state. Let me go back to some surplus asset. So this is some weight surplus here. And so what we'll actually do is we'll, if we can actually go ahead and buy that execution, we will give you credits for basically allowing you to execute certain messages. And then we'll take from that credits as we process the rest of the messages. One thing that's important to note is we do have a little bit of logic here, which says that if we only process this trader fee if the weight limit is some tangible limit. You can see here that in the comment, if the weight limit is unlimited, we actually skip this logic altogether, because a weight limit of unlimited should only apply from or should be checked ahead of time by the barrier. So something like allow top level paid execution from would already deny this kind of unlimited payment. You might actually support this kind of unlimited payment between system parachains, right? So a system parachain which skips this barrier can allow these big things, which is important. Where if we don't care about paying weights at all, or we don't care about doing it by execution, for example, you can imagine a governance parachain telling the relay chain to do a runtime upgrade. Runtime upgrades are extremely heavy, right? This kind of thing is a good use of an unlimited weight. Like, execute this upgrade no matter how much cost it takes, just do it. In that case, we are skipping over the buy execution logic altogether, because that doesn't really, unlimited execution and buying execution doesn't make sense. I can't pay for unlimited execution. So we just skip that logic altogether. So it's important that when you configure things, that you are going ahead and making sure that you are having the right kinds of configurations together. So I guess the key piece I want to take away is that it's really important that you don't just copy and paste code, that you actually do investigate deeper into the XCM executor and to understand how things are behaving, because it can be quite simple to configure things where one is supposed to check the other, but you didn't put that check there, and therefore your chain is now vulnerable to different kinds of messages and kind of attacks, right? So that's kind of one thing to take a look at. Because here the buy weight function, or the buy weight trait, the trader trait, is very simple. It has like a buy weight and a refund weight logic. And we actually take a quick look at an example of this. And you can imagine, just again in your head, let's say imagine I have the balances palette. Buying weight might be something like I have a DEX palette. Buying a weight might be something like, okay, looking at what asset you provided me, looking up in the DEX how much it's worth, saying, okay, well, this much asset, this much weight, doing the conversion, returning the weight, and returning any extra assets which weren't used to pay for the weight, right? And of course, refunding the weight would be the same thing. If I look up the asset's price, maybe for example, if you're doing a very heavy XCM message and the message does all these complex DEX or swapping mechanisms, or even like flash loan type stuff, I could look up the price after all of this stuff happened and then refund the weight that was appropriate, right? And so this is the kind of logic you can have. The more simple kind of stuff we've been doing recently, again, there aren't a lot of DEX chains out there on Polkadot, is we basically been kind of doing like a 1-to-1 ratio between like the native token price and weight. So if I go quickly into the code base and I look up this weight trader, we can actually look at implementations of the weight trader. That's dummy. Let's not look at that one. Fixed rate of counter refund. Here's an example. So here's an example of one of the builder patterns we provide to you. And this basically says, okay, well, in the configuration of this struct, you tell us, well, this much dot is worth this much weight. And so then when I look to actually buy weight, I just do the simple conversion. Like, I make sure the payment asset is the asset I expect, and then I convert to how much time how much weight I'm asking for. And I then make sure I subtract from that asset the amount of dot that I'm going to use, and then return any unused dot, something very simple like that. And again, this kind of logic is simple to start with. I think we're going to be able to iterate and have much more complex logic within the trader in the future. And again, the idea of using these abstract traits and these configurable XCM stuff is that you don't have to wait on Parity to build these next level generation things. Like, the truth is, like, Parity right now, and the people who are building, our goal isn't to build a DEX. Our goal is to build an amazing multi-chain ecosystem. Your goal as parachain developers is to build awesome DEXs, to build awesome applications. And so you can take advantage of these traits and build your own high-level custom logic into your code to make this all work, right? Yeah. Okay. So that's that. Okay. And then that's basically buying execution. So paying for weight. Okay. So now I wanted to jump into another example. So this is a little bit unprofessional, but I've been talking a lot, and I want to grab a water real quick. So I'm just going to step away for just 1 minute, grab a little bit of water, and come right back. Okay. Sorry. Ask questions. I'm going to come back and do a Q&A up to this point of my talk. Okay.
Yeah, so we got a couple of questions here in the Q&A. So you had talked about with the XCM messages, like querying DEXs. So what happens, or are there any preventions, like if there is some sort of significant price slippage between the XCM message acknowledgement and execution? Like, is that something you would have to be concerned about?
No, actually, so that shouldn't be a big issue because in the context of your chain, when you're processing an XCM message, everything happens at once. It's it's an instantaneous operation. So I can turn myself into camera full. That helps. So in terms of XCM strategy, all those XCM execution processing type stuff is all going to happen kind of at once. So as I mentioned here, you can actually do something like, check the price of the asset at the very end, and and behave things a little bit differently as a result of that. Now, when you are doing cross-chain messages, things become funny because things happen asynchronously, right? So you don't know when you send the message what happens with the network. So I think there's going to be a lot of things we're going to have to discover here. You might imagine some chains maybe support some kind of like fee range, like as long as you're within a range of fee, we will accept the message. It doesn't have to be exact, and that could be a little bit of a acknowledgement. The other thing could be that chains could all have their own account on the other on like the main relay chain, which has a bunch of assets in it. So if for whatever reason the XCM message coming in doesn't have enough assets inside of the holding, you can actually take maybe some assets out of the user's account. Or it could be that the standard that wants to be defined between these two parachains is that we don't use any holding at all, right? You could make a barrier that the very first message of any XCM is to check that it's by execution, and then your logic for by execution could be pulling assets out of the user's account. So as long as you've constantly populated an account with enough funds in it, we'll make sure that we always take the right amount of the fees from there. But I think you shouldn't worry within execution of a single XCM about slippage, because you can always handle that logic. But across XCM messages, there might be some worries there, and you're going to have to, within your ecosystem, define how you want to handle that.
Thanks, Shawn. The second question we have here is, could you send secure and encrypted data through XCM messages?
Yeah, so XCM is just like any other blockchain thing where everything has to be public. So again, these systems, in order for them to be distributed, decentralized, redundant, like all this kind of stuff, unstoppable, you need to have these things be public. That being said, the message itself can be encrypted. But how you would decrypt that message in a secure way, or how you would do that kind of stuff, like it probably involves like T's, like those trusted execution environment types things, or some ZK snark stuff, or I don't know, things way above my pay grade. But let's imagine an example where I can encode a secret message. Let's say it's like my will when I die. And I put that onto the blockchain. Now that encoded message is public to everyone, but we don't actually know what is inside that message until I reveal the private key. And then so I can have some kind of secondary service where it's like a sleeper switch, I think they call it, where if I don't trigger the sleeper switch after a certain amount of time, then the private key is revealed to the world, like an email or something like that, and everyone can then go ahead and actually review and look at that message. So in the same kinds of ways, of course, you can send special kinds of messages across XCM, but there aren't any inherent like privacy or secrecy or obfuscation layers within XCM. Everything has to be public. Those kinds of layers have to exist within your logic in the way of like T's or whatever other logic there is.
All right, I'm going to have to read this one to make sure I get it entirely correct. So pardon me if I'm not looking directly at the camera here. Is there a way to transfer an asset back to the origin chain if getting assets trapped on the destination chain without awaiting for the destination to support the asset?
Okay, interesting. Yes. So we do. This is actually pretty new. So I'm not as noted as I should be about this. But there is this asset trap thing, and the general idea is a handler for when assets are left in the holding register. And so I think at a high level, you can imagine, I think what we're looking to support within XCM is that if you send us a message that we have no idea for, and of course there's some, we have no idea how to handle it, and there are some assets inside the holding register, a bad idea would be just to drop that message, because that would basically you would lose assets into the void of time. They're not stored anywhere. So the asset trap in the most basic way, you can imagine you just take the holding register, you store it in state and save it for later. Be like, this message, I didn't understand it, but there are some assets that were included part of it. And I don't know what the assets are. I don't know anything. There's some bytes in there. I'm going to just, store it into storage, and then we can handle it later. And, some kind of governance / collaboration offline and all that kind of stuff can handle what to do with those assets. So that's kind of a catch-all. So if there's any situation where users are trying to send you messages with bad information in it or things you don't support yet, or some kind of mistake, asset trap should be able to handle all of those kinds of things. Make sure that funds don't get lost. But I think beyond that, we have the barrier ideally, which should hopefully check, are these messages at all things that I would even want to support or look at? And hopefully, some combination of barrier, asset trap will make sure that these messages don't, lose out. One thing that we are also looking to support is kind of return messages. So I think the original versions of XCM, we didn't, you could only send a message one way. You couldn't return a message back. And we're looking to lessen that a little bit. I think we have now the ability for these subscriptions and for messages to return a result at the end of the message. But you have to remember that these messages are all asynchronous, and that sending an XCM message is very expensive. So it wouldn't make, for example, sense that if you send an XCM message, and let's say that you want to transfer 2 dot. So you send 2.1 dot in order to transfer those 2 dots because you want to pay 0.1 dot for the fee. But the fee ended up being only 0.8 dot, right? Or 0.08 dot, right? So you still have 0.02 dot left over. It would not make sense, for example, to send an XCM message back saying, hey, here's your 0.02 dot left, because it would be way more expensive to send that message back than to have that. So something like the asset trap could have simple logic saying, hey, you have some leftover assets at the end of the XCM message, so this 0.02 dot, I'm going to place it as a credit into your account, right? And then you can imagine building up a credit of extra tokens, which can then be used again to pay for XCM messages if for whatever reason something happened and you don't have enough fees to pay for it, right? So all of this logic can really is really customizable by you as an individual. At the early stage of XCM, which we are right now, these kinds of things aren't super well handled, but I think we'll expect to see more and more of that happen as things develop. And actually, I would suspect, to be honest, that the parachain teams, not Polkadot, will be the first to innovate here, because Polkadot, I think our team is mostly going to be focusing on things like interactions between system level chains, right? And doing basic, reserve transfer assets, which that's the next thing I'll talk about. I think that we will be focusing on those kinds of scenarios, and so we're not going to be handling these kinds of niche, DEX transfers as often.
Okay. One last quick question from the Q&A tab. Why is your VS Code pink?
Oh yeah, oh man, you should definitely get this plugin. So I will plug this plugin, which is it's called a Peacock, and Peacock allows you to basically skin the outer edge of your thing. So I'll grab a. This one doesn't have any skin right now. I can go to command palette, and I can do Peacock. Surprise me with a random color, and boom. Now this repository, whenever I open it in GitHub, actually I'm not showing you my screen. Okay, now I'm showing you the screen. That I'll do it again one time. So I can do view command palette, surprise me with a random color. Boom, and now it's green. You can see. So basically, the idea here is I can basically, you can skin any repository or that you open up, a project you open up in VS Code with a color, and then when I do things like this, where I want to look at which project I'm working on, I can really quickly identify. Well, pink for Polkadot. I think I have like that this blue for Cumulus, like clouds, and then even for substrate, I have I think the substrate color, like this kind of green blue, like sea green type thing. Let me open the repository. Oop. Okay, didn't want to open up. That's fine. But yeah, so it's really nice. It's a really nice plugin. Allows you to identify when you're working with many different projects at once. Okay, so I'm now going to jump back into my stuff I wanted to go through. And again, if you have more questions, definitely go and ask them in chat. Oh, maybe I'm looking at my screen right now. Can you see the color? It could be that I'm not the way that the screen is cropped that you can't see. Oh yeah, you can see the green. Okay, that's fine. Okay, going back. Okay, so now we're gonna do a reserve transfer. Okay, so now let's talk about it. So the first example we did was a simple transfer. So again, we had the parachain send a message to the relay chain, but the transfer itself happened within the relay chain. So it was like a single chain transfer. We withdraw and deposit assets all within a single chain environment, consensus system. To do a reserved transfer, we're going to actually have to do things across two different systems. So the scenario for a reserved transfer, and this is how most third-party chains interact with Kusama to get KSM on their chain. So if you've done this on maybe the Karura chain, for example, you can actually send KSM from Kusama, from your account, into the Karura chain to then actually go ahead and interact with their DEX stuff and all of their cool DeFi systems. And the way it works is that when you mint KSM or the reserved KSM onto Karura, that asset is now backed by some asset which is reserved on the Kusama chain. And this is very much like a, kind of like if like the reserve treasury or like other things in the practical world, we basically have some asset where its value is backed by another real true asset. So I guess at some point the dollar used to be a reserve backed asset of gold. Now it's not, right? But in this case, the KSM on Karura is only as valuable as the KSM that's backing it on the Kusama chain. And what's important about a reserve backed asset is that, again, we want to allow parachain teams to manipulate and use things like KSM on their chain, but we can't really trust them to actually hold KSM itself, right? Like we can't actually trust them to have what would be a teleported asset. So what we say is that you are able to mint this KSM, but users who use this should constantly be aware of the fact of how much actual reserve KSM do you hold on the Kusama chain, right? And so I expect in the future, when you have these kind of UIs where you're interacting with KSM on Karura, there might be something that's actually pinging and querying like, okay, how much total KSM does Karura claim it has? How much total KSM does it actually have in its Kusama account? And if ever there was a discrepancy between these two, you might start, sending some warning signals that hey, Karura maybe has minted or lost some KSM, which it actually should be representing in its system, right? But again, with third-party chains, we do support reserve backed transfers. And so I'm going to walk through an example and kind of show you what that looks like. So the breakdown of a reserve transfer is a message that will execute in two halves. First half of it will execute on the relay chain, where you're going to be transferring this reserve asset, the Kusama, and then the second half will happen on the parachain, where it'll be minting the reserve asset on that side. And so the way we would start that message is by calling this transfer reserve asset instruction, and within transfer reserve asset, there is a parameter inside, which is itself an XCM message, which is a vector of additional instructions that should execute once the message has been received, which is like by execution and deposit asset, right? And so let me see what I wanted. I had some notes here I wanted to write. So yeah, we already talked about the wait unlimited. So note here that in this, so this code is coming from the XCM palette, which again we can take a look at, which has a nice little extrinsic for you to be able to transfer assets easily to other parachain teams. And we use that the wait limit unlimited here as a part of that. Because right now we don't know what the wait would be on all the different chains. Like if we want to support transferring the asset to all these different kinds of parachain teams, the wait could be different on each parachain. So we say, okay, we're the relay chain. We can say unlimited. You can choose if you want to support us or not. Like we know we don't care. Like you can support us in however way you want, right? The other thing we do is we do deposit asset wild all. So there are these wildcard parameters which can act on top of the holding register. So imagine that you have a parachain which handles many assets within storage, right? If you were to say move all the assets of a user, it would be an extremely expensive operation, right? You can imagine that I have, tons of NFTs, tons of different, assets, the native token, like all these other things, like a bunch of derivative assets, all these kinds of things. You could never make an operation which says move all assets. But within the context of the holding register, remember, all of the assets are already in memory. They're already kind of in this holding register. And so we can actually have one, pretty large limits for how many assets that the holding register can manage at once. And two, we can have things like wildcards that say like move all the assets because they're already in memory. Manipulating and moving them around is very simple versus having to go to all these different storage items and try to get them all. So doing things like wildcards is really nice, being able to say something like, okay, well, here are a bunch of assets that I want to transfer. Take the fee, okay? I don't know exactly what's going to happen at the end, after the fee is taken, but whatever is left over, move the rest of those assets over, right? And so a wildcard all is one of those things like saying like, okay, well, you're going to be doing some operations onto the register. Whatever the current state is at this point, move it all to the over to some other spot, right? And so that's what this wildcard is. And this is a pretty unique and powerful tool in terms within XCM to allow you to kind of handle, kind of unknown behavior within the XCM message, right? And then, of course, these are the kinds of messages that we execute onto the relay chain. When we actually go ahead and process this transfer reserve assets function, what we'll actually do is append on top of it two other messages: reserve asset deposited and clear origin. And then we will actually go ahead and send that message to the parachain. So let's actually quickly jump into this instruction. And then we can actually walk through a little bit of this. And actually, before we do that, let's just run the function. I like starting first with seeing it work and then trying to understand what's going on. Okay, so yeah, we ran the test. The output, I think, is a little bit easier to read here. This same output, but basically you can see that we're processing all the instructions. So in order to do a full reserve asset transfer, the first instruction is transfer reserve asset, which has, again, these the multi-asset inside of it and the instructions, all that kind of stuff. It has, we look at the holding. Next, we see on the other parachain, reserve asset deposited, clear origin, by execution, and deposit asset. So now let's go ahead and take a quick look at what's going on here, and we'll walk through that example. Okay, so first I'm going to go to reserve asset. Oh, it's transfer reserve asset. Right? Transfer reserve asset. And we're going to go to the XCM Executor. Let me find it real quick. Sorry. It's hard to work with such a big screen. Where was I working? This XCM Executor. This is what I'm looking for. So this and this. Okay, cool. So again, on the relay chain, I'm going to initiate the XCM message transfer reserve asset. And this is going to go here, execute this logic. It's going to process the assets that I want to do the reserve transfer for, right? It does some checks, like make sure that, okay, it's relocating the assets so that when you send the message, the destination chain understands what the assets it is, right? It processes the assets, does any type of logic it needs to do to actually, reserve the asset. And then it takes, 2 additional instructions: reserve asset deposited and clear origin. It takes the messages that you want to execute after that, appends that to these messages, and then all of this then gets sent through XCMP. This message gets sent through XCMP to the destination. So if I wanted to do a reserve asset transfer from Kusama to, let's say, Karura, I would go ahead and set the destination as Karura, select my asset as KSM. It would go ahead and this beam asset would go ahead and move the KSM from my account into the Karura account. And then it would take these instructions and then make a new XCM message and send that via DMP, a downward message passing, to Karura. Now Karura will now receive a brand new message, which is this reserve asset deposited, clear origin, and the other 2 instructions I have. I think I've written that down somewhere. Let me make sure if I have or have not. Let me see this one here. Yeah, I've written this down here. So by the time we get to Karura, we now have a new XCM message and a new context which we're processing the XCM message. And the XCM message that Karura is seeing is reserve asset deposited, the assets, clear origin, by execution, deposit assets, right? So now let's take a look at from the Karura side what we'll actually be doing. And one thing I want to note, I guess maybe could be a little bit confusing, and maybe I should do an improvement from this workshop, is that when I look at this output of the instruction logs, I'm actually looking at 2 different chains. Right here, where my mouse is, the instructions here are being executed on the relay chain. The instructions after this are being instructed on the parachain. So one thing I could do here is I could have a log message, which logs when I'm entering and exiting instructions executing on different contexts. But note that all 4 of these instructions are happening on the relay chain. I think the origin should maybe specify that, right? Yeah, the origin is, you can actually kind of see that in the origin here, where the origin of the message is parents 0, and it's coming from an account. So I'm initiating the reserve asset transfer, and it is coming from my account, or this 0 account in this message. But then when Karura receives the message, the origin of the message is actually parent 1 here. And that means it's the parent of Karura, which is the relay chain, which is Kusama, right? So here you can kind of see that already. But note that these are, again, 2 different execution contexts. So let's go back. So now the next thing we're going to be looking at is now what happens. So Karura now has received reserve asset deposited. So let's take a look at that instruction, what it's going to be doing. So now we have reserve asset deposited. So first, the first thing we do, like any good check should do, is like, should we even accept these assets? So these assets are coming to us. They're not in the holding register. They're actually just a parameter of the XCM message itself. So the XCM message itself could say reserve asset deposited, a bunch of different assets. What we want to verify is that the origin where it's coming from is an origin where we trust it to be a reserve asset. So you can imagine where I sent, I think personally, an XCM message from my account directly to Karura saying, hey, mint me a bunch of KSM. Karura would say, hell no, I'm not going to do that because I don't trust your origin. You are not the reserve asset, like a reserve chain that I would trust. But if I do this reserve, starting with the relay chain, and the relay chain itself is sending the message to Karura saying, hey, Shawn is trying to reserve some asset. He did do the proper things. trust me, Karura can say, okay, well, the origin now is actually the relay chain, and I do trust the relay chain to be a reserve asset here, and therefore I will process this. And what the very important part of this reserve asset is it transfers the asset from being a parameter in this XCM to actually moving it into the holding. And again, when anything in the holding account is like fair game, like this is like a real asset in the eyes of XCM, and you can do fees on it, you can transfer it, you can mint asset based off of it. Like the holding account is the real deal. So we want to make sure that anything that moves assets into the holding account is like verified and trusted, and all the words we need to do to verify that this is not being manipulated by other users, right? So we are getting the message again. The origin from here we saw was coming from the relay chain, and we have configured the parachain to support accepting this as a reserve transfer. Okay, and then once we put it into the holding, bam! Now we can start doing the cool stuff. The first thing we want to make sure though is we want to make sure that and we can start doing cool stuff. We can start executing the messages that were defined by the sender itself. So remember, back here, when I sent the reserve asset transfer, I actually was able to define the other operations I want to do. So I'm sending the message. I'm the one sending my tokens from KSM to the Karura chain. I want Shawn to get the Karura reserve tokens. So I will define in the deposit asset function, move the assets to me, the beneficiary. So I will have a different account on Karura. Like I can have, the same account with the same account ID, or I can even have a different account, and I can define that as the beneficiary. So when on Karura, when they are minting the reserve asset, they will mint that into the correct account. So these are the additional operations that happen after the fact. But we want to make sure that between us putting things in the holding and us executing the operations that the user wants us to execute, that we clear the origin. That right currently, when we do this reserve asset deposited, we have a very powerful origin. We have the relay chain origin in context. So if the user started doing a bunch of other operations, and you were checking that the origin was the relay chain, and it started doing a bunch of, it would elevation of privileges here. It would be really bad if the user could define a bunch of operations that would act using the origin of the relay chain. So we clear origin, saying, hey, the rest of the operations, we can't assume anything else about the origin, or we don't need to assume anything else about the origin. And then we can do things like buy execution, deposit asset, etc. I do want to note that there is another instruction, which is in here. I think it's like set origin. Yeah. Or descend origin. And descend origin is a way actually that you can actually populate the origin with a different kind of origin that is a subset of the power of the origin of the current origin. So you can imagine that the relay chain says, okay, at this point in time, don't clear the origin. Instead, go to change the origin to the origin of the user who's making the call. That's the kind of, as long as not an elevation of privilege, we can go ahead and do those kinds of operations too. And then, of course, executing things would be in that context. But for buy execution deposit assets, we don't need any origin. These operations act only on the holding. So as long as assets are in the holding, we don't need any more, authentication or authorization to be able to do things. So now we've moved the assets into the holding. We pay any fees, and then we simply deposit the asset. Any assets are in the holding, we move those all into the beneficiary account. And it's that simple. And that's what we're seeing there. I want to talk a little bit more about the is reserve. So as I mentioned here, we check that it is reserve. One of the builder patterns that you'll see is commonly used is this filter asset location for a native asset. And so we basically can have a filter here that says we support any chain and its native asset. We will allow you to be a reserve for that asset. So as long as the asset that you're sending us is a concrete asset with your ID in it, with your parachain ID, we'll say you're a reserve asset. So this will support, let's imagine a statement has this configuration. We will support Kusama being the reserve back of a Kusama reserve token. We will support Karura being the reserve back of a Karura reserve token. We'll support Moonbeam being a reserve back of a Moonbeam reserve token. This is a very abstract thing that supports all kinds of parachains that everyone can mint their reserve token using their concrete asset, right? And yeah, and again, as I mentioned, we're able to accept this at all because as we saw inside of the logging, that the origin coming here is parent one here. That is the first parent of the receiving parachain, which is the relay chain. And we see that the instruction is actually to deposit an asset of multi-location parent one here. So we are trying to deposit an asset where the origin is there, and therefore this filter passes the test, right? So that is some very powerful stuff that we can do here. Cool. And finally, I want to talk about the teleport transfer. So there isn't much actually new to talk about here, other than just the differences between a reserve back transfer and a teleport transfer. So again, a reserve back transfer is something that we can do between kind of untrusted chains, because we make sure that the asset that is actually being minted on the other side is should never be thought of as the real asset. It's only thought of as a representation of the real asset, which actually continues to live on the concrete holding chain. A teleport asset is different. A teleport asset is where we actually move the asset itself onto a new consensus system. And this is the kind of thing that we can do between system parachains, right? So system parachains, where there's a higher level of trust between, the logic between these things, we can actually go ahead and actually move KSM itself from the relay chain into state mine, right? And then state mine itself can then do things at a higher elevation of privileges with this asset, because it actually owns that asset, and actually, it actually is like holding this real asset. That asset has literally been teleported to a new location. Now, practically speaking, the steps of this is the same, except for basically, one, we have a different path of logic handling a teleport. So, exactly what it means to teleport an asset could be different. You can see in the reserve asset deposited, let's go back. We actually have, where is it? All right, I can't, it's not in my notes right here, but there's this thing called beam asset, which actually does the transfer. Here in teleport, we have a checkout. So this is a different logical branch you can do to handle what it means to teleport an asset, right? And then, of course, there's some XCM messages, or XCM instructions, which are specific to things like receiving teleported assets, initiating the teleport, stuff like that. And of course, there's also going to be additional, you can imagine, configuration here, which verifies, okay, there are some chains that support as a reserve, is a reserve chain. But this one is there's a different set of chains I support as a teleport chain. So there's a completely different configuration where it says, like, do I support this as a teleporter chain? And usually those are only system level chains, right? But practically speaking, in terms of execution, it's very similar. We send this initiate teleport. That itself will have an XCM message. On top of the initiate teleport, we will add to it receive teleported assets in clear origin. We will then append any of the messages on top of that to this, and then send the XCM message to the parachain or wherever we want to send the message to. Then the message on the parachain side at that point will look like this: receive teleported assets, clear origin, by execution, deposit assets. So basically all of the same things, except we just have a different set of instructions around teleporting versus reserving, because these are kind of two different levels of privileges in terms of accessing and doing things in XCM. Yeah, and so those are the main things I wanted to touch on. So again, these are the three key kinds of scenarios that you can imagine what will happen in the early days of XCM and Polkadot. Hopefully, you can see that within XCM, I've kind of it's a very heavy onion. Like, I mean, and I think it really all starts at the XCM Executor and the configuration. That the XCM Executor itself has all of these different instructions and that you need to process, and all of those can manipulate the behavior based off the configuration. The configuration itself has a bunch of different points and entry points where you can configure things, and within the configuration, we have these builder patterns, which I've been kind of like hinting at, which allows you to easily configure how exactly you want things to behave. And of course, you don't need to use our builder patterns. You can go ahead and create your own builder patterns and create your own execution logic or things. Or even, I mean, I don't know if this will happen, but maybe one day someone will actually just build their own XCM executor altogether and just have their own executor do their own things however they want, right? So really, is peeling back the onion here. As long as you're able to kind of navigate things, as long as you're able to do logging, like what I've shown you here within the XCM Executor, use things like the XCM Simulator to process and test your different scenarios, see if what you're expecting is actually what's happening, you're going to be able to learn very quickly how XCM works. And once you get a handle of things, I think it's going to be a very powerful tool for the future of, this multi-chain ecosystem we're building. Right? So that's most of it. I think, is it right, Bill? I have like 7 minutes left to answer questions.
That's right.
Awesome. Then let's do that while I drink some water.
Okay. Yeah. While you're drinking water, just a note: the Q&A tab somehow got cleared. So if you did have a question, please add it back in. But I actually had a question. So I understand on a single chain how you can verify the origin of a message, but could you explain a little bit about how we can ensure that the origin of these XCM messages actually is from the chain it says that it's coming from? Right.
So this is all defined by basically the XCMP, like the message protocol on Polkadot. I'm gonna oversimplify it, but I caution that I might be wrong because I don't know exactly the implementation details here. But you can imagine basically that when you establish being a parachain with Polkadot, there's all this kind of like a handshake that needs to happen, like matching the Genesis hash, accepting the messages from the right parachain, like all this kind of stuff that needs to happen, right? But every single parachain on Polkadot is given its own kind of channel, and this channel, in terms of processing messages, basically, when I receive a message from the channel, I put it into a special storage, and this storage marks which parachain it's coming from, and then I'm able to process that message, and then because it came from this channel, and this channel is only available to this parachain, therefore I can know that who it's being sent from. Like imagine, I'm trying to think of a good analogy, but imagine that Bill, you and me have a walkie-talkie where only you and me have this channel. If you hear a message on that channel, like if it's a Morse code, it's from Shawn because it's you and me have established ahead of time. It's only between you and me talking. So basically, we're able to identify the origin of a message based off of which channel the message came through. And now, of course, things like the relay chain sending us something, like the relay chain. When I receive a message from the relay chain and I'm a parachain, practically speaking, I should, it is kind of like it's my parent. It's my dad. I should basically do whatever it tells me to do. So if I say, do X, Y, or Z, or to, instead change it from this origin to another, or a more common example right now with the current version of XCMP, that the relay chain acts as an intermediary between sending messages. So if I'm parachain A, want to talk to parachain B, currently parachain A sends it to the relay chain, and the relay chain sends it back to B saying, hey, I got a message from A for you. The long-term XCMP is looking to remove this. So right now we have XCMP Lite, which uses the relay chain as an intermediary. In the long-term, XCMP plans to be directly messages between A and B, so you don't have to handle this. But right now, if the relay chain says, hey, I got a message from A to you, you have to trust the relay chain. Like if the relay chain wanted to lie to you, it could just stop being it could stop letting you be a parachain, right? It could just disconnect you from the chain. So at that point, it's not really a lot of sense. So that's the kind of how you will look at and identify origins.
Okay.
Yeah.
Because of the channel.
Yeah, exactly, because of the channel. And then one more thing is that obviously you should do sanity checks. Like, if parachain A is sending you a message and says, hey, actually, I want to be the relay chain, like, no, that you don't accept those kinds of messages. So obviously.
Yeah. You can't have someone try to say that they're your dad when you're not. They're not. That they're
exactly.
not.
Yeah, that's what they tell kids, right? That to don't walk away with strangers.
Right. So will the Spree module change the way that XCMs are done?
Yes. And you'll notice right now a lot of XCM, unfortunately, still has some kind of trust there. And, these are, blockchains and Polkadot in general are trustless systems at a certain level. Like the protocol itself is trustless, and all these game theoretical things makes things, kind of trustless and, economical. But I will say that right now, in order to know that things are behaving properly between two different chains, you have to have trust in there because you don't know exactly the logic that's programmed on the other side of the chain. What Spree solves is Spree says that the logic which would execute a message is shared and fixed between two different consensus systems. So how do I say this? Like, if you wanted to have some kind of interface layer where you wanted to manage balances, you want to make sure that whenever balances are being transferred between two parachains, that always the same behavior is happening, and that one parachain isn't just doing some crazy thing like minting 10 times the asset that you sent me. What Spree will do is Spree will say, okay, here's a wasm blob. This wasm blob will define basically a balances palette. It will define a simple version of balances palette which handles the state of this asset we're tracking. And this exact same wasm blob will exist on both sides of the messaging system. And so we send messages, because both sides have the exact same wasm blob, I can, without any trust, verify, or without any trust, know for fact that when I send this message, it will exactly execute exactly how I expect, right? And so Spree will basically introduce between XCM a shared pieces of logic, which will remove all trust layers needed between different consensus systems. For the time being, again, we're not quite at the Spree level yet. This is an iterative process. We are using a sense of trust that chains are behaving well. But of course, we have governance, which can always step in if people start misbehaving. That XCM channels or XMP channels are all optional. So if you're a parachain, you choose the other people you want to form channels with, and usually those kinds of forming of channels involve, collaborations, trust, and like working together with humans to make sure that these channels are working together well, and other such things. But Spree really will be the next step of bringing a trustless and yet verifiable message execution for XCM.
Okay. We have one last question here. The question is, if the relay chain is L0 and parachains are L1, why is downward message passing relay chain to parachain and upward message passing the other way? Wouldn't it make more sense vice versa?
I think that's just a numbering system. I think that in the context of our visualization, we have the relay chain at the top and then layers go down, like kind of like a pyramid. It's funny. I just watched a video recently from Vertasium about Celsius and the guy who invented the thermometer. And originally the original Celsius scale, boiling was at 0, and then freezing was at 100. And so the scale actually went opposite, right? And the reason he did that was because, in the real world where we would use a thermometer, you don't walk outside and it's boiling, right? But you do walk out and it's below freezing. So, having, it go up in that direction, makes it easier for having to avoid right negative numbers and all this mathematics. So in this sense, it's just a numbering system. It's downward in our mental model is from relay chain to parachain. If you were to have it the opposite way, or if you were to number it the opposite way, Polkadot would be layer infinity, right? Because it is as low as it gets in terms of setting everything up. But it's just a naming system. You can make a PR if you want to change it.
Yeah, I like the idea of Polkadot as layer infinity.
I like it too.
Yeah. All right. Well, thank you very much, Shawn. This was really insightful. I learned a lot from this. Hopefully, everyone else did too.